Good morning, everybody. We are Taekwondo B and Taekwondo from the team Light.DarkZero. Today, we are going to present our work based on the paper by Eric Wong and J. Cotter. In their papers, right, they are actually proposing a new mechanism that is probably robust against the non-bounded adversarial perturbations on the training data. The idea is to consider a convex outer approximation of the sets of the activations retrievable from the non-bounded perturbations and devise a robust optimization procedure that minimizes the worst case loss over these outer regions. So in simple term, right, is making like we have the input which is allowed to have some perturbations, and when we pass inside the deep neural network, right, we simply extract the last layer of the activation functions, and then we construct a convex outer bound using those functions, and with that we can classify the adversarial samples which lies beyond the outer bound, and the benign samples which definitely lies inside the boundaries. So this one is achieved in their code, right, using a dual neural network. So what we do here is we are trying to test whether this mechanism is work across the domains. So right here we have a CNN architecture on the audio classifier. So you can get the data sets here, which I have shared in my Google Drive, and it is actually used of the urban sound data set. So it consists of roughly 10,000 samples inside the data set. And then before we actually build the model, right, because we have the audio file, and our CNN architecture actually used for image classifier. So we have to transform the audio into the image file. So how we do that is use the Fourier transform and to compute the Mel spectrogram of the audio file. So here, in order to convert the things, right, we have to learn about what is inside the audio file. So basically, the audio file has two important properties, which are the frequency or sample rate and also the amplitude. So how we do this, right, is because we want to mimic how the human perceive the sounds, right? Because human perceive sound on a logarithmic scale. So meaning that when your frequency is decreased or increased on the logarithmic scales, human can detect that, but not on a linear scale. So we actually use a Mel scale to replace the frequency, meaning that it's a logarithmic transformation of the frequency into the Mel scale. And also we use the decibel labels to transform the amplitude into its logarithmic scale also. So with the two scales and also the Fourier transform methods, we are able to produce a Mel spectrogram of the audio file. And then this is how we do the actual transformation inside our code. We have actually you can look at the code for details. And then we also implement a class for extracting the audio file from the datasets, because actually the datasets comes with a CSV file that help us to locate the audio file, and we can just extract the audio file based on the location, and also we can straight away perform the transformation on the audio file to get back our image size. And this is how we do the training datasets and also the validation dataset or testing dataset. We actually split them into a 2x using a 2x split, so that we got roughly 9,000 samples on the training datasets and roughly 2,000 samples in our testing datasets. So this is the loader. Take note that we actually only use the batch size of X, and our original image dimension would be something like this after the transformation. However, the best setting for the classifier to work at its optimal state, right, is using a larger dimensions, which include more important information. This one cannot be achieved because we have the limitation on the GPU memory provided by the Google Colab. So we have decided to reduce down the dimension so that we can fit into the memory constraints. However, this would have some effect on the classifier. So because of the loss of some important information inside the input image. So how we overcome this is we increase the number of epochs during our training. Yeah, so before we get down into our training process, right, we have to build a model. So our model is a very simple CNN model where we have 4 convolutional layers here. And for each convolutional layers, we have a ReLU activation functions and also followed by a normalization functions. And then in order to account for the non-linearity in our model, right, we actually use the Chi-Ming normalization or Chi-Ming initialization in our convolutional layer. And then after that, we have a flattened layer, which will combine all the neurons together into one single neuron. And we output the prediction using a linear layer, which will help us to determine out of the 10 classes whether this particular image belongs to which classes. So this is our training process, and we are using the cross entropy loss as our loss function and our Adam as our optimizer. We have a scheduler for us to assist our training. And for this one, inference, right, we actually are doing the evaluating the model based on our testing data sets to test whether the model is overfitting or it doesn't perform well in the region outside of the training data set. So here is our training result, and we can see that using 20 epochs, we actually achieve around accuracy of 80%. However, with the greater dimensions we use, right, we can actually achieve roughly similar the accuracy or better within 10 epochs. Yeah, so this is the drawbacks where we reduce the dimensions. So this is basically just to test our model, and this is the attack we have here. So this one is the fast gradient method attack, and this is a projected gradient descent attack. Both of these attacks are actually a white box attack that make use of the gradients of the model. That's why they are actually compute the perturbations, which is best suited for this testing mechanism. So after we launch the attack, right, we can see that our model, right, with normal training, right, it doesn't have any security property. So it gets fooled by it misclassified for almost all the images under the attack. So yeah, so how we can overcome this, right, is to make use of the defense mechanism proposed by the original authors. So here we reset the models, and then we have to make use of 2 files provided by the original model authors. So the 2 files are the dual.py and the affine.py. The dual.py is mainly focusing on constructing the dual neural network and also the robust training inside the file, while the affine.py is actually focusing on constructing the layers inside the dual neural network. So take note that because the original code is specifically designed for an image of square size, we do not have a square size input here. So we have to change the dimension inside the code. And also we have to, when we do the upsampling using the transpose operation, right, we also have to specify the output dimensions in order to fit our desired dimension. So in order to do that, right, we actually have to build another neural network inside that will help us to do the upsampling and give the exact output dimension that we want. So in order to avoid the network affecting the training process, right, we switch off all the gradients of the networks. Other than that, right, during the robust training, right, we actually compute the masking of the images so that we can find the best adversarial boundaries. So however, the masking in the original code only works for the one dimension class. So we have to obtain 10 classes. So how we solve it is we simply repeat the same mask for the remaining classes. You can look for the implementation inside the 2 file shared in the Google Drive. And then this is how we do the robust training. First, we actually train the model as usual, but we call the robust loss function inside the dual.py in order to train the model using the dual neural network. And after that, we actually test the model directly here in order to save the memory and also to test whether our result is valid or not, because the training process is taking very long time. So we decide to do here. After that, we also try to attack the model directly to see if the defense is actually working. So here are some of the results we obtained from our training process. And then, yeah, so this is the final result we obtained. So we actually run a toy example which samples 2000 samples from the original data sets. So we actually obtained a reduce in the error using the when the model is presented with the adversarial samples, right? We managed to reduce the error down to similar to the original accuracy achieved by the model itself. So this toy example actually shows that the defense mechanism is working here. However, to further improve the models, right, we actually need to increase the number of epochs, or we have to increase the dimensions of the input images so that more important information is provided for the model to learn. Yeah, so after that, we actually run the models, the training process on a full data set, which is roughly 9,000 plus images. So this is what we have as our results here. So actually the result doesn't satisfy, it's not satisfying. And we try to fine tune our model using the epsilon parameter here. What this epsilon is actually a measure of the distance between the data point and the boundaries that we have computed. So within the distance, right, we have to make sure that there is a certificate for the model in order to classify whether this is actually an adversarial sample or it's just a benign sample. So we can see that when we decrease the epsilon, right, meaning we decrease the distance, right, we actually achieve a better robust loss and robust error here. However, we see that the original loss and also the original error is high. So it means that we are sacrificing the capability of the model to correctly predict the images in order to achieve the security. This is not what we want. So we try to increase the epsilon. However, we see that, yeah, we need more training process in order to achieve something similar to what we can achieve using a smaller epsilon here. However, the result is promising. Yeah, we can see from here. Note that when we launch the attack, right, it doesn't really defend the attack at all. There could be a reason here is because we do not have enough training yet. Because we are seeing the decreasing trend, even though the training epoch is reaching 60, we can still see the decreasing trend inside our robust loss and also the normal loss. So this decreasing trend means that we actually haven't reached the minimum of the loss functions. So this could be the reason that we cannot achieve the security here. And another point to note here, right, in order to improve the performance, right, we definitely need more computational power and memory, because so that we can we can include more information inside our input image so that the model can learn better. Another point is that we have to deal with the scalability problem described in the original paper, because currently our implementation doesn't take into account of the non-linearity of some of the layer, for example, the batch normalization layer. So they are excluded, so it will affect the prediction of the model itself. That's why we cannot achieve a better performance. So we basically have two problems to solve here. One is the scalability, so that we can, under the memory constraint, we can still train with a larger input size and also a larger image size, a larger network with the non-linearity layers included. And another one is about the memory constraint and computational power constraints. So that's all from me. However, we can see that the result is promising, meaning that the defense mechanism is actually working across the domains. It's just that we have to find the best choice of the echelon and also the memory and also the scalability problem to be solved. So that's all from me. And right now I will pass the mic to my teammate Quanting to explain the remaining parts of our work. Thank you.
Thanks, Kwambi. So we have seen that Kwambi have done a very excellent job on defending the adversary training on the closed domains. So now back to the simple questions. Can we perform the defense on a simple image classifications? And if so, how can I do it? Do I need to redo all the functions as complicated as what Kwambi have rewrite in order to fit in the model? So actually, no, we can have a quite simple way to use the convex adversarial code to perform the adversarial training on our model. So in the code itself, they actually provide several examples on how you can actually use the code. However, they're actually quite complicated because the Python file are actually run by a bash script shell that have a lot of command line arguments, and you need to pass all the options, and then it's actually quite complicated. So for these sessions, our customization is aim to simplify the usage of the codes so that we can use it easily on any custom dataset and model. Okay, at the same time, we also want to manipulate and fine-tune the parameter to find the best result we can obtain. So the result will be tabulated and analyzed in the later sessions here. So we can see here, first thing first, we can just easily git chrome from the their repo, okay, and download necessary requirements, and also we just try to fix the path problems by importing the file. And then we can start to prepare our own custom dataset instead of using the default dataset like for the MNIST or the Cypher demonstrate in their own example. We can actually prepare our own dataset. So here's an example dataset I've used. So I have so you can go to the Google Drive here to get the dataset here by creating a shortcut into your own Google Drive. And then, so for this dataset is an animal dataset. Inside this folder, you have 10 more subfolder which label with different animal names as well. And each folder actually contains around 500 of the image, animal image. So there is a total of 5,000 image to be trained and tested. So however, due to the Google Colab memory limits, we are unable to load the large image of 500 here. So what we have to do is that we need to pre-process first in order to resize all image to 16 by 16. So any size beyond here will causing a CUDA out of memory problems. So 16 times 16 is our image size. And then we will then split all these image into a testing set and the training set. So 4,000 for the training and then the rest 1,000 for the testing. So again, due to the memory limits, the training best size we can have is 32 here. So because we have the smaller image, so we have the 32 best size here. So you can see here, after you have created a shortcut in your drive here, you can then mount your drive and unzip the file to obtain the data set here. So after you got the data set here, we want to pre-process it before we use it, right? So we have a simple pre-process to first resize it into a size here, and then we try to reorder the channel of blue-green red into a standard red green blue here. Okay, and then we also have the data loader that try to load that into batch. So first thing first, note that our data set is in terms of folder of image path, something like that. So we want to have a image of data of image, and then for the label is actually their folder name. So we want to tidy up to create a dictionary and to do the stuff like that. So here is just simply transpose the image to change from the height white channel into a channel height white, something like that. Okay, so then we also use the scikit-learn preprocessing library to label and to use the label encoder to encode the label class. And also lastly, we have the train test splits. So we, as I said just now, we have a function to create a folder dictionary. So here we just simply try to resize into 16 by 16 here. And then we try to split into a train dataset after the preprocessing. So please note that the data loader here, when I split into a train dataset, they actually split it in terms of X train and Y train. In other words, I actually have the data loader for the data train and the data loader for the label train, something like that. So as for the data loader for the X train and the Y or X test and Y test. So we can check the shape here before we process. So the training have 4,000 and then the testing have 1,000, and then the side of the image have 3 channel and 16 and 16 is all good. So now we want to combine the data loader into just one. So here is where we combine the X train and Y train into just a single data loader, and X test to Y test into a single data loader here by using the TensorFlow data loader here. So here, as what you say, the batch size is 32 here, and then we just have the single train loader and the test loader here. So this is where we create. Next, we will create the model here. The model we are creating here is a simple model here that try to simulate the LabNet here. So we just simply have 3 convolutions layer, where the first layer have 3 filter of kernel size 5 times time. The second layer have 16 filter of kernel 5 times time, kernel size 5 times 5. Lastly, the last convolutions layer have the 1,020 filter of size 10 times 5. And each convolution is accompanied by the dilute activation function as well. And then we will flatten all this into a full connected layer of 1,920 neurons. Lastly, we just before we end the model, we just try to dance it linear into a 84 neuron, and then lastly try to linear into a 10 neuron, so that 10 neuron can represent the number of class we have for the classifications. So this is the learning rate for our model, and our optimizer is the Adam as well. And you can see from the summary, this is the output shape for each layer. So the main part of our customization today here is the robust training. So what we want to do is actually we can simply import a trainer file from the Convex adversarial codes, where this trainer file contains very 2 important functions, which is the train robust and the evaluate robust written for you already. Okay, so you can just simply call the functions here. What you need to just to set out the tunable parameter, which is your number of epoch, and the epsilon as described by Kwambi just now, the mean of the epsilons. So then you can just run for each epoch the training and the testing here. So this is what it will show you out for display the information for it. So it will show you the number of epoch and then the time and the average time taken. So the current robust loss and the average robust loss inside the bracket. So as the robust error, the loss, normal loss, and the normal error. So we have tabulated the result as follow here after we have tried several attempts with different parameter here. So what we try first is actually a 30 epoch with 0.1 epsilons. So you notice that the error is really bad. They have misclassified 91% of the image after the robust trainings. So which is quite bad. So we then proceed to reduce our epsilon to 0.01, and we realize that there is an improvement on our robust error. It reduced to 75%. At the same time, we increase to the 60 epoch due to the excess computation power. So however, we notice that we actually occur overfitting problems here. You'll notice that for the average training robust loss is 0.9, which is quite low. However, when it comes to testing, the average robust loss started increase to 3.7, which is relatively high, indicating there is an overfitting problem here. So the problem occur here may due to the large number of epoch. So we proceed to reduce the number of epoch and further reduce the epsilon value. So you notice that after reducing the epsilon value, the performance improved again to 68% of the error rates for the robust trainings. However, the overfitting problem is still there. So again, we try to reduce the number of epoch and the epsilon value to 0.01. So after 30 epoch, we will see that again, we have an improvement on the robust error. So for now, we can almost classify half of the adversarial image correctly. So the robust error is 59.9%. However, again, the overfitting problem is still not solved yet. So the quite high robust error here and the overfitting problems here may be due to the data side problems. Remember, our training data contain 4,000 of the image, which is actually relatively low compared to the default dataset or like Kwambi dataset of 10,000 of image. We only got 4,000, which is quite low. And for each image, the size is only 16 by 16, which is actually quite small. The resize may actually reduce some important information in the image. So again, for the memory limit actually have causing the worsening the performance here. So with a more powerful GPU and more memory limit allowed, we might get a better result here. And then improvement might be using a more advanced model like efficient net and so on, which is much more complicated in the more hidden layer. So this is the demonstration of how you can use the convex adversarial on the image classification with a simple way. So again, you can use that on your own custom dataset and your model as well. You can just simply replace the model creation part and the dataset preparation part into your own things. Then you can always defend your model with the convex adversarial with just few trainings here. So now we want to move on to the demo of idea on other things. We actually have quite a few idea on other things how we can attack them. However, due to the time constraint, we can't demo all of them. So we just demo for the disrupting defect by the team like Goodnight. So what they are doing here is they try to using the adversarial machine learning to prevent the defect problems. They actually try to induce the perturbance into an original image so that the disturbed image that contain the noise cannot perform the defect well. So what our idea to attack them is that first we will upload the original image for them to put in a perturbance to generate the disturbed image, and then we will try to run the defect on both original and disturbed image for the comparison later. Then thirdly, we will upload the disturbed image again to perform the denoising on it, try to denoise the perturbance induced by them, and we try to download the denoised image. Then we upload again a denoised image to perform the defect to check whether there is an improvement or not. So here is what we have done. First thing first, we try to get clone from their repo, what they have done so far, and we obtain the download pre-trained model from them as well. Then we upload the original image to the collapse and try to generate the disturbed image here. And you can see that we actually download the disturbed image for after generations. So then we proceed to testing the defect on both original and disturbed image. So here is the running code to test the defects, and you can see that they actually perform a image to image translation using a star gun to change from the original feature to, like, for example, black hair, blonde hair, brown hair, female, or the old, something like that. So this is using the original image, and you can see that there is the defect generated is actually very realistic. It's quite natural and it's quite difficult to distinguish whether it's a real or fake, something like that. However, after the noise induced inside the disturbed image, you can see that it's quite easy to differentiate now, because you can see now the defect generated, there is some bright region around the nates and the cheek there. So by using this, probably you can differentiate quite easy these defect things. Okay, so what we want to do is try to avoid all these black regions around here. So we then upload our disturbed image download from the generation just now, and we try to perform the denoise. So what our denoiser is actually taking from the backspot denoise backspot smoothing here. Okay, we give from their repo and try to download their pre-trained model here, so we can have the denoiser ourselves. Okay, so this is just a function to pre-process the image and to convert back into the image. And then this is where we loaded our denoiser. After we have loaded our denoiser, we just simply denoise, smooth our distracted image to become a denoised image and try to download it. And then after we got the denoised image, we can test it by uploading first, and then we will try to run the defect, the star gun, the defect to check out the thing. So this is the result we obtained. So here is the tabulations of the result for the ease of comparisons. So for the original, it's actually quite well. And for the denoised image, you can see compared to the original, actually not really good, because again, I can still see some shaded things here. Okay, but when you compare to the distract image, it's actually much more natural, because they won't be like a big chunk of black thing. It's more like a shaded, something like that, a shadow, something like that. So we see an improvement on this. So we believe that with further fine-tuning of the denoiser, we can eliminate most of the noise and have a better defect result as similar as close as the original defects, something like that. So that's all for our presentation today. So feel free to explore our final collabs here. And thanks for watching. See you.
See you. Thank you.